Dear students, today we are going to discuss rotational spectroscopy. It is also known as microwave spectroscopy. The main content of today's presentation include rotational spectrum of rigid diatomic molecule, an expression for moment of inertia and rotational energy levels, selection rules for rotational transition, and a problem to calculate internuclear distance. Finally, the intensity of spectral lines. Rotational spectroscopy is mainly concerned the transition between condensed rotational states of a molecule in gas phase and the molecule which interact with microwave region of electromagnetic radiation of wavelength 1 centimeter to 100 micrometer. The condition for a molecule to be microwave active is the molecule must have permanent dipole moment. An example is HCl, CO, OCS. In case of this kind of molecule, for example in HCl, the plus and minus charge changes periodically and the component of dipole moment in a given direction fluctuates regularly. This fluctuation is exactly similar to the fluctuating electric field of radiation. Thus, the interaction can occur and energy can be absorbed or emitted, and the rotation give rise to spectrum. But in case of H2 and Cl2, there is no such charge separation. That is, the molecule has zero dipole moment, and hence such molecules are microwave inactive. Rotational spectroscopy is usually given by gas molecules. However, in case of solid or liquid molecules, they do not show rotational spectra due to the strong intermolecular attraction, and hence no free rotation is possible. In other words, rotational motion is quenched due to the collision between their molecules. Rotational spectroscopy is only practical in gas phase where the rotational motion is quantized. Here we consider two types of molecule. One is called rigid rotor or rigid diatomic molecule. Rigid rotor means that when a molecule undergo rotation about the center of gravity, the bond length of the molecule doesn't change, that is, the bond length is fixed. But in case of non-rigid rotor, the bond length increases as the angular velocity increases. And here is an expression for moment of inertia as well as energy levels of a rigid diatomic molecule. Consider a rigid diatomic molecule of masses m1 and m2. They are joined by a rigid bar of length r0, that is called its bond length, and r0 is equal to r1 plus r2 when the molecule is rotating at an axis at the center of gravity c. So we can write by balancing equation m1 r1 is equal to m2 r2. Also the bond length r0 is equal to r1 plus r2. So the moment of inertia about the point C is given by I, that is equal to m1 r1 square plus m2 r2 square. From equation 2 we can write m1 r1 is equal to m2 r2. So substitute instead of m1 r1 by m2 r2, and instead of m2 r2 we can substitute m1 r1. So this equation will become m2 r2 r1 plus m1 r1 r2. So r1 r2 into m1 plus m2. From equation 1 and 2 we can write m1 r1 is equal to m2 r2, and r2, instead of r2 we can substitute R0 minus R1. So the equation will become M1 R1 is equal to M2. Instead of R2, we are substituting R0 minus R1. So the equation will become M1 R1 is equal to M2 R0 minus R1. And expanding, M1 R1 is equal to M2 R0 minus M2 R1. Therefore, we can rewrite M1 plus M2 into R1 is equal to M2 R0, and we will get the value of R1, that is equal to M2 R0 divided by M1 plus M2. Similarly, we can calculate R2 from the same equation, that is M1 R1 is equal to M2 R2, and we are substituting for R1 from this equation, that is R1 is equal to R0 minus R2. So we can write like this: M1 R0 minus R2 is equal to M2 R2. Expanding, M1 R0 is minus M1 R2 is equal to M2 R2. Therefore, M1 R0 is equal to M1 plus M2 into R2, and R2 is equal to M1 R0 by M1 plus M2. So we got this value for R1, R2, and this value of R1 and R2 we are substituting in the equation I. Then finally we will get an expression for moment of inertia, that is I is equal to M1 by M2 by M1 plus M2 into R0 square, that is equal to mu R0 square, where mu is called reduced mass of the system, and the value of mu is M1 M2 by M1 plus M2, and R0 is the bond length. So this equation defines the moment of inertia in terms of atomic masses and bond length. Next, we are going to write an expression for the energy levels of rigid diatomic molecule. The energy levels of rigid diatomic molecule is obtained by solving Schrodinger equation, which is given as Ej is equal to h square by 8 pi square I j into j plus 1, and energy is expressed in terms of joules, and the value of j is 0, 1, 2, 3, etc. Usually the rotational spectra is discussed in terms of wave number. So we know that E is equal to hc nu bar, and nu bar is equal to delta E by hc. So we can write this expression in terms of nu bar, that is a wave number that is usually expressed in cm inverse, centimeter inverse. So nu bar is equal to epsilon j, that is equal to Ej by hc. So we'll get an expression like this: h by 8 pi square Ic j into j plus 1. So just remember, the rotational energy levels are expressed in joule, it means Ej. When it is expressed in cm inverse, it means that nu bar. So an expression for Ej is h square by 8 pi square I j into j plus 1, and the expression for nu bar is that value divided by hc, that is equal to h by 8 pi square Ic j into j plus 1, where h is Planck's constant, I is moment of inertia, c is the velocity of light in centimeter per second. You have to remember, c is velocity of light in centimeter per second, and j is called a rotational quantum number. It can have value from 0, 1, 2, 3, etc. And this expression we can write this term h by 8 pi square Ic is a constant, that is called b. Instead of h by 8 pi square Ic, we can rewrite as b. So the expression will become Ej is equal to, or epsilon j is equal to Bj into j plus 1, and b is called a rotational constant, and the value is h by 8 pi square Ic in unit centimeter inverse. So these are the rotational energy levels of a rigid diatomic molecule, and we know the energy levels is given by the expression epsilon j is equal to Bj into j plus 1. When j is 0, we can substitute the value of 0 for j, then epsilon j will become 0. When j is equal to 1, When we substitute, we'll get a value of 2b. When J is equal to 2, we'll get an energy level 6b, and J equal to 3, the energy will be 12b, like that. Then 20b, 30b, and 42b for J equal to 6. Just to remind, the energy levels are not equally spaced. The lowest level is 0, then 2b, then it is 6b, then 12b, 20b, 30b, 42b, like that. And when J equal to 0, the energy is epsilon J is equal to 0, and we can say that the molecule is not rotating at all. This is called 0 point energy. So, in order to consider rotational spectrum, we have to discuss about the difference between the energy levels. For the rotational spectrum or the rotation transition, there is a certain rule that is called selection rule. So, the first condition is that the molecule should have permanent dipole moment. It is denoted by mu. It should not be equal to 0. The second condition is delta J should be plus or minus 1. It means that the transition to next higher state is only possible. All the other transitions are forbidden. We can see from this figure that the transition from to next higher state, that is 0 to 1, is allowed, or transition from 1 to 2 is allowed, 2 to 3 is allowed, and the reverse also, that is the absorption, and the reverse means transition from 2 to 1, it also allowed, that is called emission, or 3 to 2, that is also allowed, it's called emission. And those kind of transitions are allowed, not the transition from 0 to 2 or 2 to 4. These kind of transitions are forbidden. That is called a selection rule. So in order to discuss about electronics rotational spectrum, we have to find the difference between these energy level. For the transition from 0 to 1, the amount of energy absorbed is the difference between these two energy level. That is, for the J to 1 transition, delta epsilon J is equal to epsilon J first level minus epsilon J zeroth level. That is, the difference between these two is 2b. For the transition from 1 to 2, the amount of energy absorbed is 6b minus 2b, that is 4b centimeter inverse. And the transition from 2 to 3, the amount of energy absorbed, or the energy difference between them, is 12b minus 6b, that is 6b. And 3 to 4, the amount of energy absorbed should be 20b minus 12b, that is 8b. So like that we are getting spectrum like this: 0 to 1 2b, 1 to 2 4b, and 6b, 2 to 3 transition, 3 to 4 8b, then 4 to 5 is 10b, like that. In generally, we can write an expression that the transition from J to J plus 1 state, we can write like that: the energy difference between J plus 1 state minus energy difference between J state. The energy of J plus 1 state we can write like this: substitute instead of J by J plus 1. So we will get an expression like that: B into, instead of J we can write that J plus 1 and J plus 1 plus 1, that is J plus 2. This is the energy of J plus 1 state minus energy of J state. Energy of J state is given by Bj into J plus 1. So if you are expand, we will get like this: B into J, J square, 1 plus 2, 3J, 1 into 2, 2, minus J square plus J. So when we solve this equation, we will get like an expression for the transition from J to J plus 1 state is given by nu bar J to J plus 1 is equal to 2B into J plus 1 Cm inverse. 2B into J plus 1. So we can simply calculate using this equation for the transition from 0 to 1. 0 to 1 transition, we can substitute the value of j is 0. 0 to 1 transition, the value of j is 0. Okay, then it will become 2b into 0 plus 1, that is equal to 2b. For the transition from 1 to 2, the amount of energy absorbed should be 2b into, for j we should substitute 1 to 2 transition, jth level value, then it will be 4b. So this is the rotational spectrum of rigid diatomic molecule. We are getting a line spectrum, and we can see that these lines are not equally indensed. That we'll discuss in the next slide. And we can see that the density are different for each spectral line. And one thing is that the energy difference between the spacing between these spectral lines is 2b in all cases. That is, difference between 2b and 4b is 2b, 4b and 6b. The difference between the spectral line is always, it is equally spaced, that is 2b sine inverse. Next, we are going to solve a problem to calculate internuclear distance of a rigid diatomic molecule. So the question is, the first line in the rotational spectrum of carbon monoxide is 3.84 cm inverse. Determine moment of inertia and bond length. So the given that the first line, we already studied it, the first line occurred in rotational spectrum is at 2b. The given value of 2b is 3.84 centimeter inverse. So we can write b is equal to 3.84 by 2, that is equal to 1.92. That is the first step. Next, we have to calculate moment of inertia. So we have to know the relation between moment of inertia and rotational constant. That is, b is equal to h by 8 pi square ic. And we can write in terms of I is equal to h by 8 pi square bc. And the value of h is 6.626 10 to minus 34 joule second divided by 8 into, and the value of pi is 3.14 square into value of b is 1.92 centimeter inverse, and c, just remember c, the velocity of light, should express in terms of centimeter per second, that is 3 into 10 to 10. When we calculate, we will get a value of 1.458 into 10 to minus 46 joule second square. The joule second square is, we can write in terms of kilogram per meter square, that is joule is equal to kilogram meter square second raised to minus 2. Then we are substituting for joule. We usually moment of inertia are expressed in kilogram meter square. And next thing is, we have to calculate bond length. So the relation between moment of inertia and bond length is I is equal to mu r square, or r is equal to square root of I by mu. So I is, we already calculate, and next we have to calculate mu, the reduced mass. So the reduced mass is calculated by the equation m1 m2 by m1 plus m2. Here the compound is carbon monoxide, so mc into mo, oxygen, by mc plus mo. We know that atomic mass of carbon is 12 and that of oxygen is 16. So when we are substituting here 12 into 16 by 12 plus 16, that is equal to 6.85 atomic mass unit IMU. So we usually express mu in kilogram. So we just converting 1 IMU. 1 IMU is equal to 1.66 into 10 to the minus 27 kilogram. So 6.85 IMU is equal to 6.85 into 1.66 into 10 to the minus 27 kilogram. That is equal to 11.4 into 10 to the minus 27 kilogram. And this value and the value of I also substituted in this equation, we will get an expression for R. That is, R is equal to not I, R is equal to root of I by mu. Then we will get a value of 1.13 into 10 to the minus 10 meter, and that will be equal to angstrom, that is 1.13 angstrom. So we calculate the bond length of 1.13 for carbon monoxide. Next, we are going to discuss intensity of spectral line. The intensity of a spectral line, that is the intensity of rotational spectrum, is depend on the population of energy levels. The population is dependent on, or it is expressed by two terms. One is Boltzmann distribution, and the second one is number of degenerated energy levels. Boltzmann distribution is given by an expression that is equal to Nj by N0 is equal to e raised to minus Ej by kT, and we know the energy level equation, that is equal to e raised to minus Bhc j into j plus 1 by kT. We know that Ej is equal to Bj into j plus 1, and we can write, we should multiply by Hc to get the energy value, that is Bhc j into j plus 1, where N0 is the number of molecules in j equal to 0 state, and Nj is the number in any higher state. Now we just going to calculate the value of, or the population at J1 state. For example, a typical value of B is 2 cm inverse, and at room temperature we just going to calculate the relative population in the J1 state, that is N1 by N0 is equal to e raised to minus, and the value of B is 2 into H is 6.625 into 10 to minus 34 into C 3 into 10 to 10, and the value of J is 1 into J plus 1 is equal to 2 divided by kT. K is the Boltzmann constant, and the value is 1.38 into 10 to minus 23, and we are calculating at the room temperature T, and it is in Kelvin, is 300 Kelvin. So when we are substituting this value, we will get that N1 by N0 is equal to 0.98. It means that there are almost as many molecules in J1 state as in J equal to 0 state. That is, J0 state and J1 state are both equally populated. As the value of J increases, when the value of J increases, there is more rapid decrease of Nj by N0. That is, the population decreases. When the value of J increases, the population of each energy level is decreases. Also, we can see from this relation that Nj by N0 is exponentially proportional to B. Right? That means that when the value of Nj by N0 decreases, when the value of B increases, is given by a graph like this. This is a graph by plotting Nj by N0, that is e raised to minus Bhc j into j plus 1 by kT against rotational constant number j. We are getting a plot like this, that is, a population decreases with the increase of j value. Here we are just comparing with the 2b value, and one is shown by square with having b 5 cm inverse, and another is circle having b 10 centimeters. When the value of b increases, the population is decreases gradually. So as the B increases, the population state again decreases. So next factor is the number of degenerated energy levels. Degeneracy is the existence of two or more energy states which have exactly same energy. In case of a diatomic rotator, we approach the problem in terms of its angular momentum. An expression for energy and angular momentum is given by E is equal to half I omega square, and P is equal to I omega, where I is the moment of inertia, omega is the rotational frequency, and P is the angular momentum. And from this equation we can write omega square is equal to 2E by I, and omega is equal to root of 2E by I. Substitute the value of omega in this equation, then we can write like that P is equal to square root of 2EI. So we know that the value of E is h square by 8 pi square I j into j plus 1. So we just substitute for E, we'll get j into j plus 1 h square by 4 pi square. Therefore we can write P P means that square root of 2a, that is a square root of j into j plus 1 into h square by 4 pi square. That is equal to P into root of j into j plus 1 into h by 2 pi. That is the angular momentum is the integral multiple of h by 2 pi. That is, we can write that P is equal to root of j into j plus 1 unit. That is, the P is quantized. It means that P has a magnitude as well as direction. So when j is equal to the first state, the value of P is root of j into j plus 1, that is equal to, substitute for j by 1, we will get root 2. That is, the magnitude of angular momentum is root 2. And since it is j equal to 1, it has 3 reference direction, that is the plus 1, 0, 1, minus 1. All these directions have same value for angular momentum. It means that at j equal to 1, the energy level is threefold degenerate. That is given by this figure. It have 3 directions of angular momentum: minus 1, 0, plus 1. And the magnitude of each direction is root 2. Hence, when j equal to 1, the rotational energy level is equally energized. That means that is a triply degenerate or threefold degenerate. When j is equal to 2, the value of angular momentum is root 6, and it can have 5 directions, that is minus 2, minus 1, 0, plus 1, plus 2. When j equal to 3, we have 2 root 3, and they have 7 directions, that is minus 3, minus 2, minus 1, 0, 1, 2, 3. That is, j equal to 2 is a 5-fold degenerate, and j equal to 3 is 7-fold degenerate. You can given in this figure is a 5-fold degenerate when j is equal to 2, and it is a 7-fold degenerate. So it means from this figure that the number of degenerate level available increases rapidly with increasing j value. So when we conclude, the molecular population in each level that decreases exponentially. Also, the number of degenerate energy level increases rapidly with j. Therefore, the relative total population is given by is proportional to both factor. One is Boltzmann distribution, and another is degeneracy. When the j value increases, the Boltzmann value decreases. When the j value increases, degeneracy increases. So the total population is given by, that is proportional to 2j plus 1 into e raised to minus ej by kt. When we plot this population against j value, a graph that shows a maximum population at a certain j value then diminishes. The differentiation of this equation shows the population is maximum at the nearest value of j. The maximum population is given by root of kt by 2 hcb minus 1 by 2. Also from this graph, it is clear that the line intensities are directly proportional to the population of rotation levels. The transition between the levels with very low or very high j values will have small intensity. The intensity will be maximum at or near j value. The intensity is maximum in between low and high j values. That is given by the expression j is equal to root of kt by 2 hcb minus 1 by 2. And here is an assignment related to this topic, and you have to solve all these problems